Federation of Electron Microscope Societies, now IFSM, ever since 1962, and in fact was its 5th member at that time. EMSI is having total membership close to around 2000, around 1800 something, from vastly different disciplines like materials, biological, medical, metallurgical, forensic, agriculture, geological, and so on. The CSIR Advanced Materials and Process Research Institute, Bhopal, in short AMPRI, was formally established in the year 1981 as one of the constituent labs of Council of Scientific and Industrial Research, CSIR, similar to CNRS in France, dedicated for carrying out research in the area of lightweight materials, smart and functional materials, nanostructured materials, waste to value-added materials, and rural technologies and water resource management. So today's speaker, and to the best of my knowledge, among few first speakers under the banner of EMSI through webinar so far, Professor Christian Colliex is presently Emeritus CNRS Research Director, Orsay in France. He is known for doing adventures with atoms and molecules, implying electron microscopy, and more precisely, electron energy loss spectroscopy. He was in Cavendish Laboratory in 1976, Arizona State University 1985, IBM Researcher San Jose 1986, and he was director M.A. Cotton Laboratory, a CNRS lab during 1996-2002. His main fields of research concern the development of new instrumentation and methodologies for local analysis in condensed matter, relying mostly on electron energy loss spectroscopy in electron microscopy. He has published more than 300 papers, with many in Science, Nature, PRL, Nanoletters, and so on. There are several awards and positions to his credit. If I start listing, that may become a full lecture itself. He has been laureate of French Academy of Sciences during 1995 to 2005. He has served from 2007 to 2011 as president of the International Federation of the Societies of Microscopy and as president of the International Conference on Microscopies, IMC 17 at Rio de Janeiro, 2010. Today, Professor Colliex will speak on new views on the Nano-World offered by Hyper-spectral electron microscopy. To know more about Professor Colliex, I request you all to go through his most recent entitled interview, that is entitled Adventures with Atoms and Molecules, published in Microscopy and Analysis, May-June 2020, very recent. So with this brief, on behalf of Electron Microscope Society of India, CSIR Advanced Materials and Process Research Institute, and also on my personal behalf, I welcome you all for your gracious presence in today's lecture. As I understand, dignitaries, members of EMSI, I'm hearing Professor Chattopadhyay's voice, I can see Dr. G.K. Day, and so many dignitaries are there. And many important researchers from Professor Collier's group also have joined for today's lecture. I welcome all of them. And now may I request Professor Colliex to deliver his presentation. Professor Colliex, please.
Thank you very much.
Thank you.
Okay, so I take off my mask so
yeah,
that
sure.
you hear me much more clear. So thank you very much, Avanish, for this introduction. And I am very happy, of course, to deliver this first talk on electron energy loss spectroscopy. So hello to all of you who are listening to me, colleagues, friends all over India. You are locked down at home or in your laboratory by the pandemic. So have a good day, and I hope that we will spend a short hour together, speaking of electron energy loss spectroscopy. So here is a picture with Amanish, which was taken a few months ago, just 1 month before the beginning of the lockdown period. So it was the APMC conference in Hyderabad, which was very well organized, and I was happy to have been invited there. So let's come now to our subject. The subject is Nano-World. So what is Nano-World? Nano-World is very broad and very diversified. So I have selected here a few pictures, not that recent, but showing where in the lab the different colleagues and researchers are working on which subject. So you can see dopants clustering in oxides, growth of growth of graphene layer, electron doping at interfaces between two oxides, silver nanorods. This will be plasmonic and nanophotonics, 2D materials resolution, and also some biological materials, and these are nanodiamonds in cells. So this is a very diversified world. So what are our tools with an electron microscope? An electron microscope, it has an incident ITV, 60 to 100, 200 kilovolt beam. And in a scanning transmission, the beam is focused on a small probe on the surface of the specimen. So you have this incident beam coming on, coming on the specimen. So there are what I call primary events. Okay, primary events, that means that the electron coming is scattered and is deflected, inelastically scattered, or giving some energy, losing some energy when it goes across the specimen and is inelastic scattered. But when it is inelastic scattered, it has created excitations there, which can disappear in electron hole pairs in emission, secondary emissions of electrons, X-rays, visible light. And there, on this textbook for material science, David Williams Bergkarter figure, I have put what are the main sources of information when this electron comes across the specimen. So you can have, with the elastically scattered electrons, annular dark field, high angle, or annular bright field imaging. And then is inelastic scattered electrons. When you measure the quantity of energy which has been lost, you have EELS spectroscopy. And when looking now at the emission, you have EDX, emission of photons in the X-ray domain or in the visible domain, which is cathodoluminescence. So now, what do we need to learn at the nanometer and atomic scales in your specimen? You need learn what is the crystal structure, the position of atoms, and there you have mostly diffraction or imaging with the different channels of imaging. You want to know the nature of atoms under the probe, and then you have the signal coming from the electron energy loss spectroscopy or from EDX, emission of X-ray. And you have also electron states, that is charge bonding. How are the atoms bonded to neighbors atoms? What is the charge transfer or the symmetry of the bonding? And finally, we want also to know physical properties, transport, optical, magnetic, at the best level. So to do that, so I will discuss mostly in this talk. This channel we will use EELS, of course, which is also discuss and cathodoluminescence, which are the major source of information. Okay, so how practically in Orsay we studied these signals and we recorded and used these signals. So we use dedicated scanning transmission electron microscope for, you see, 40 years now. The first one, the VG, came in Orsay in 1980, and it is still in operation. You see on the left, the VG microscope, which you will see below the instrumental characteristics called field emission source, energy resolution 0.5 eV, spatial resolution 0.5 nanometer. There we have developed spectral imaging acquisition and processing. And recently now it's not too much used in EELS, but mostly in cathodoluminescence and liquid nitrogen stage. So we have there the sketch of the microscope, a confirmation source, focus on the specimen probe, which is typically of this side, sub-nanometer. You have annular dark field detectors to collect the signal for the topography, scattered electrons. Then a magnetic spectrometer, which scatters and which measures the energy loss which the electrons have suffered during the transmission through the specimen. And detectors, and basically over all these years, it was a couple photodetector followed by an electron detector. This microscope has been working over more than 35 years, and one major responsible for this success is Marcel Tancé, one of our collaborators, long-time collaborators in the group, and which has always maintained this machine at the top level. And so with this machine, we could deepen our knowledge and use of STEM in EELS. Now, recently, of course, this microscope was no longer of the top, the most advanced machine. The aberration corrector and the monochromators have come into a new generation of machine, and we could acquire during the last decade successively an aberration corrector neon ultrastem, which you see there in its box, and more recently in 2018 an aberration corrected and monochromator neon Hermes, and this was done with Tempo's project, which is behind there, and the leader of this project is Odile Stefan. So now, so what's the difference between the VG, now what is the basic diagram of the last chromatem microscope which we had in Orsay? There is always a high brightness electron source, cold field emission gun, then a high resolution monochromator, which selects which selects a narrow energy beam there, which filters and selects, and there is a correction aberration corrector probe, which focus so on the specimen, which focus a beam within a probe now, which is of the order of 1 angstrom now, and we can select a very narrow energy resolution bandwidth on the primary beam, typically in the 10 milli electron volt. So after the specimen, so there is a selection of detectors, angular detectors, which can bring you different images. And for instance, you see on the right an annular dark field image when you use the largest, the broader detector. And after you have the EELS spectrometer, aeration EELS spectrometer and detector. So typically for one electron, you have a bright field, a dark field, which gives you the structure, the position of atom, a map, which gives you analytical signal. And now, before the specimen, there is a system which picks the light, a mirror, elliptic mirror, which picks the light and takes it out into cathodoluminescence spectrometer and detector. So basically, if you have a triangular metal nanoparticle, like the one you see on the right, you can get simultaneously the annular dark field image and the EELS map or the cathodoluminescence map of the same effect. So you will see how important it is in the future. So basically, now I move to hyperspectral to explain why I use this word in the title. So if you have the information, typically on one point, that is on a narrow spatial domain, delta X and delta Y around a point, and within an energy window that is delta X of energy loss, then you have an information which is a bit of information, a 0D bit of information. If you measure at this position a spectrum, so with many many channels in energy. You have a 1D information object, which is an electron energy spectrum at one position. You can also select one energy and then filter an image. So you have a 2D information. But what is the most important now is that if you collect for all the position X, Y on the specimen and all the energy domains, you have a 3D object, which is a 3D data object. So, and this is what is a spectrum image. And I call it hyperspectral imaging because now you have an image of the specimen, but with many different energy windows, so hyperspectral. And in this slide, which summarize what is information carried in an EELS spectrum, you have an EELS spectrum of an MGO sinfold or cube. And in this energy spectrum, which extends from 0 to 1000 eV, you have many different signals. So if you look at the core energy losses, the blue domain on the right, there you have you are equivalent to X-ray domain or soft X-ray domain. But if you go close to the zero loss, which are the electrons which have not lost any energy, so we are going to 0 and to the infrared domain. So you are a very broad spectral domain from infrared to X-ray domain. This is what I call it hyperspectral because it extends to, and you can get for all positions on your specimen an information in the different channels of energy. For instance, in the band gaps at around 6 or 7 eV in the case of MGO, and now very recently on the phonon modes, as you will see at the end of the talk. Okay, so from early to present. Now I will look in more detail a little about the information and the fields you use for the different energy spectral domains. For instance, a spectral domain which corresponds to core energy loss domains above 50 eV, or from low energy loss domain from 1 to 30, and ultra low energy loss domain below 1 eV. So let's start from an old story. So in the 90s, so this was the beginning of the use of spectrum line. So we began with spectrum line. That is, you have an image, annular darkfield image, which shows a carbon nanotube in white, the two walls of the carbon nanotube, and in the center in gray, is there something? And to see if there is something, the idea is to move the spectrum from A to B, so this was a line across the specimen, and to collect all the spectra, which you have on the left from A to B. The most important signal is the carbon KH at about 285 eV. It has a lot of fine structures, but what you see more interesting is that in the center of the object, so you can relate very well the information signal, the spectral signal, to the position it comes from. And so you see that in the center of the tube, there is some nitrogen. So nitrogen, this is the nitrogen signal at 400 eV. And on the spectrum, you see very nicely this nice signal at 400 eV. So it was a good demonstration. And in this period, that in 1990s, this was a great success of EELS, because EELS, which was a study of interactions and excitations, came to something which was very important to characterize nanostructures. And in particular, this was a great period of nanotubes. And together with the Japanese groups, we had several collaborations for years there with Sumio Ujima, Pulika Jayan and Kazu Suenaga. We studied, for instance, in this case, a sandwich carbon boron nitride carbon tube. You see the spectra and of the boron and carbon, and when you plot the profile of the intensity of the boron and the carbon and nitrogen, you see that you have boron and carbon outside, and boron and nitrogen in the center overlap together. So the model can come to quantitative representations, counting layers, 3 layers of carbon, 6 layers of boron nitride, and 5 layers of carbon. So this was really the moment where the first real success came from nanometer size analysis with EELS. So let's go another another example, and to change a bit from nano objects, we go to some nano analysis of biological specimens. So this is, again, what is the technique? You see, you recognize the 3D object, spectrum and position on the specimen. The specimen is a section and biological section, and we probe the probe and we perform spectral microscopy. So for the identification of the peaks that you see, you have the position of the different components from the intensity, abundance of this, and from the shape, the maps of the local environment. So this is the work done by Marta de Frutos in our group. So this is conventional dissection. She is working on kidney calcifications and in particular on rondel plaques. I did not know myself what it was before discovering these beautiful images. So what you see in this section, conventional, you see arrowed by red or blue arrows, you see very small objects. When you look at them with annular dark field stem, there are two lines of images there. So there are 10 objects like that. And some of them are surrounded by blue lines and some of them by red lines, because if we perform EELS analysis on these different nanoparticles, you see them on the right. On the red ones, you have phosphorus very clearly at about 150 eV and calcium at about 350 eV. In the blue particle, there is none of them. Uranium is just a staining product, so has not big application. So from there, after identifying the main elements, so you recognize again this spectrum with phosphorus, calcium, and nitrogen, which are the main object. Nitrogen is important because it shows that you have organic material. It is bound to carbon in biological material. So these are the maps of three different particles. In the first two, you see that you have phosphorus and calcium. Inside, something which is more organic, as the nitrogen map shows. In the last one, you have a mixture of them. So to go further, like this, it's a more detailed analysis. I will not go into detail, but you look that the signal are changing. For instance, the phosphorus, the carbon. In the carbon, I have on the top, in the figure B, you have a carbon in blue, which is related to calcite. This is phosphate carbonate, and another one, which is apatite, which is, I don't know what I say, calcium carbonate, which is calcium phosphate. So it is very difficult. And then you see clearly that in the carbonate, you have a peak E, which is very a good demonstration on the carbonate CO peak. And then when you move, you can use it to recognize, determine where is the interface between organic and mineral particles. And from there, the authors have developed models for nucleation and formation mechanism. So let's come back to more Nano-World signal as we know them traditionally in a solid-state physics laboratory. So there, with this core, how far can we go? So we demonstrated in 2000 that the limit, we could identify one atom. So this was the figure on the right, on the left of this. So you had a special specimen made of gadolinium stain carbon 82 molecules with one gadolinium atom filling the inside of single-wall carbon nanotube. And from there, we could show that with the gadolinium signal, we could count the number of atoms in different clusters. So there was not the model structure above under the beam. The beam was 100 kilovolt. 100 kilovolt was too strong for this specimen, was beginning to destroy and to induce clustering of atoms. So these are the results demonstrated in 2000. Kazuo Suenaga continued on this, and on the in Japan, and on the right part of the figures, there are two of these atoms within clusters, a lanthanum and a cerium. And when we look at the fine structures and the position of the peaks, we can distinguish in particular cerium 3 plus and cerium 4 plus. And in this case, the signal was showing that the cerium atom was a cerium ion of 3 charges. So here it was an image, and there the signal, the limit was the sensitivity, the signal to noise at this level. Let's move to more crystalline material in oxides. And in this case, which has been recorded now with an ultra-stem machine, there are 2 crystals, one of strontium titanate above one of lead titanate. And lead titanate, and there the demonstration of the good resolution in space and signal, and there are many pixels. So the pixel is typically 0.005 nanometer square. So 1 pixel, you see the curve on the right, the low bottom curve. So you see the peaks of the titanium L23, so L3 and L2, separated by side symmetry. And there, when you take 1 square and you instead of taking 1 pixel, you see what is the signal of 4 by 4, 8 by 5, and you see that the signal to noise becomes very good. And for 6 angstrom by 6 angstrom, this is a very good signal to noise. Other information. So now, if you move to the right part of the picture, we go and see how this titanium. You have titanium in both oxides. So titanium in strontium titanate and titanium in lead titanate. So you have strontium titanium everywhere. And if we follow the square there and the peaks, you see that, for instance, there is a small change in the L3 peak, in particular in the splitting between the 2 components of the L3 peak. And then that brought some theory and more study and what was the reason of this change of splitting. And this was, it came out with the theory that it was due to tetragonal distortion from cubic to so there was, so you see that there are on the left, you have reference peaks for strontium titanate and lead titanate. And if you see in detail on the L3 and L2 edge, that there is a change of splitting between both. So this was studied in detail by DFT calculations done a few years before by Almudena Torres Pardo in the group. And you see that this change of splitting between, if you look at figure E, you have a paraelectric strontium titanate in black and ferroelectric lead titanate in red. And you see that the difference of splitting is clearly explained and demonstrated by these calculations. Another example in an oxide material in tubulate cobaltate. This is a complex specimen developed in Caen by people in Caen and studied in our group by Laura Baucher, who is supporting me during this talk. So you see, there are simple things. So you see that there is bismuth, strontium, cobalt, and oxygen. If you look at the annular dark field image, you see clearly square of very bright spots. The 4 spots very bright are due to the bismuth, which is a heavier element. And then there are between them, there are medium contrast dots, which are due to strontium and cobalt. So the contrast is not very different between them. But if you look at the EELS spectra, you distinguish them very well because the cobalt L23 is very different from the strontium M23. So we can perform images where you have the cobalt map. So you see the cobalt map is between 2 strontium map and the final figure in color, you have also the oxygen, which is in red. We see if you have looked in detail at the contrast of the atomic columns there. But let's go further. Let's focus on the cobalt. And when you now you have localized the cobalt columns very clearly, and you see that you see 4 distinct cobalt sites, which are marked by blue, purple, red, and green, separated by 2 5 angstroms each of them. You see that we are going very locally. This is the annular dark field map to see them, and then when you make the cobalt map, you see very well. And along one line, you try to see if there is a change between the different atomic columns, and consequently, what you see the maps in purple and red are different in position from the maps in blue and green. So there are 2 distinct electronic configurations. And one step further is to make a decomposition, a spectral decomposition using, as it is mentioned on the top, vertex component analysis, which are mathematical tools which are becoming more and more useful now when we have big data, many data. So you can distinguish 2 energy component maps so that the blue and red are associated with the cobalt 3 plus, and the other 2 are associated with cobalt 2 plus. There are 2 spectral compositions, and finally there, the difference in fine structures is not due to difference in environment, but the difference of charge. There is a charge transfer which is different in the 2 atomic columns. So we learn a lot of things. This is what we could do with core loss spectroscopy. These core loss edges, their position, and their intensity, and their fine structures. So let's move now to plasmons. Plasmons is a major excitation which is created by an electron going through a thin foil. So on the left there, you see bulk plasmon in silicon, and this is a very old spectrum, which I recorded maybe 45 years ago, 50 years ago. So, and it is on the screen, cathode tube. And what you see clearly, you see 1p, 2p. So these are 3 spectra on specimen of different thickness, 50, 100, 250. So it means that for 50 nanometers thick, you can excite with your electron, which is a 100 kilovolt electron. You can excite one plasmon when going through the specimen. 200, you have 1p, 2p, and 250, we can excite 1p up to 5 or 6 plasmons. And the energy loss for 5 or 6 plasmons is 100 eV. The plasmon loss in silicon is 16.6. Oh, this was a subject which was studied in the 50s, 60s. But I was very much surprised, and I like much the paper when it came out. You see in Science in 2015. This was a group from California, which used the plasmon in bulk to measure the temperature. So I was asked to make a perspective, and it brought my interest on that. And so these pictures show what is it. This is experimental setup. No, should not. No. Yes. Okay. Good. Very good. Wonderful. Okay. So you see the experimental setup. It was with a quite standard microscopes, 80 kilovolts, no monochromector, no corrector, a lot of current, and a full width of zero loss at 0.85 eV. The spectrum acquisition time was 2.6 milliseconds. And then what you see in the center of the features, you see a spectrum in the figure B. You see a spectrum in figure B with a zero loss at 0. This is aluminum now. So, and you see plasmon of aluminum at 15.2.3 eV. So the point which was clearly used there, I am trying. Okay, it's just okay. Okay, why do why does I don't I okay we have a small problem to shift. Okay, okay, thanks. You see that the position of the peak E is proportional to the square root of the number of electrons, n, in the formula in the center of the figures. So n varies with temperature, because if temperature increases, the material delayed, so per unit of volume, there is less electrons. So there is a shift of the plasmon peak when you heat the temperature. And this is what you see there between the temperature at room temperature and at high temperature. So basically, this is what has been done here. There is an electric circuit which is heated there, and from one box there, from one box there on the bottom left to the bottom to the box of the top right, there is a difference in color which corresponds basically, you see, the equivalent estimated in the box is the first one is 310 K, and the top right is 390 K. So you can measure a change of temperature of 80 with accuracy of a few degrees. Okay, so that was about the bulk plasmon. Let's come now to localized plasmons, and now this has surface and interface plasmons. So this is the slide which shows two basic case. So when an electron goes across a thin foil extended medium, it excites a bulk plasmon. This is what is written there. And the solution, the value is defined by the zero value of the dielectric constant. When you take a thin foil and your electron is moving parallel to the surface, this is the second case, you have the surface plasmon, you excite surface plasmon. So this was well studied. With spheres, now this is another surgery, the surface plasmon on a sphere. So that was the me case. And then let's go to more complex specimen like a triangle. What will be the energy modes in a triangle? Okay, so this is a work which has been done in our lab about now 15 years ago by Jason Nelaya in his PhD, supervised by Mathieu Kossiak. So let's see, we have a triangle, silver prism, you see it on the analog dark field image, and we record spectra all over this triangle. And when you look at the spectra, now we are working in an energy range around the visible, because it goes from about 2 to about 3.5 eV. And you see that depending on where you are, your plasmon is shifting from the near infrared to the UV. This is clearly when you look at spectra along a line ACB, along the ABCB, you see clearly how are the position shifting. So this was a basic study of how localized are plasmons on particles. And maps of these peaks are plotted just below, and you see clearly that you have a special mode on the tip, a special mode on the edge, and a special mode inside. So this has been a lot of studies following that in many places around the world. And we call these resonators, because these resonators have different shapes and aspect ratios. You see on the top left image, 4 resonators, triangles, a small one, 4, a big one, 3, or now narrow wires. So, okay. And then you see maps and images. So this has been the beginning of a lot of studies associating cathodoluminescence and EELS to study the distribution of electric fields generated around these structures by the incident electron. Here is one of the most recent one that has been done in the lab. Again, a triangle, but now it's an aluminum nanotriangle, 600 nanometer, very large one. And then you see that you can see different edge modes and breathing modes. So this is a map. The edge modes are 1, 2, 3, 4, and you see the triangle where these are modes which are on the edges of the particle, so 5, and you have modes in the inside of the particles, which are breathing modes. Okay, expanding now, we are going to the final energy domain, the deep infrared, so the below 1 eV, and you see that with the monochromator, which is now installed on the chromatem machine, the zero loss can be bring down to below 5 millivolt. And what's most important when you look at it intensity in a log scale, a logarithmic scale, there you see that at 1,000th, you can have reduced the signal of your tail to a low level. Consequently, you can look at the plasmonics in long copper Nano-World. I don't know how long is this one. You see the scale up, it's a few microns long. And you see that you can, as a follow, as a spectrum analysis, you can look at surface modes, low energy along, and typically you have in 1 EV, you can have up to 10 modes. So it is now modes in the 100 millivolt instead of the 15 EV that we were looking at the beginning. So with this good energy resolution, very good energy resolution, bringing you can study a lot of physics now below 1 EV. And below 1 EV, vibrational spectroscopy has culminated along during these last 5 years, for instance. It started from the paper by Krivanek and his co-workers in Neon. Sorry. Vibration spectroscopy. In this paper by Krivanek in Nature, he has demonstrated that you can see peaks around 100 millivolt now, which is quite different from what we were studying in the beginning, which corresponds to photons in different solids. Another example by the same group, 1 year later in Arizona State University, compares a nil spectrum of a guanine crystal when you place your electron beam just outside your crystal, not to destroy, to damage it too much. And you see that in this energy range between 0.2 and 0.4 EV, you have exactly the same spectrum as when you send, you make an analysis, Fourier transform infrared analysis on a large area of the specimen. It is beginning to open a new field, and new field is mapping photons. So mapping photons, this is the first study 2 or 3 years ago by Lagos and Batson on an MGO nanotube, and there you can see that it distinguishes two modes at 70 and 77 millivolt, and you can map these two modes along the corner on the edge surface of the carbon nanotube. In our group, Xiaoyan Li has performed similar measurements on two main MGO cubes, and it shows clearly that these two peaks at 70 and 77 millivolt are located on the edge or on the surface of the carbon nanotube. These spectra have been acquired at 1 millisecond per spectrum there, and for each image, each spectrum. So there is 750 by 50 pixels and 50 images. So it opened the way to 3D mapping on photons on an MGO nanotube. You see that the MGO tube has been tilted from the sequence on the top, the cube length in 190 nanometer, and you distinguish very well the corner, edge, and face modes, the three-dimensional curve by Shoyan Lee and collaborators in Orsay and in Austria, which is this beautiful image on the right. Okay, another final very elaborate experiment which has been performed now is we know plasmon with no phonon. Is there any, how can we see if plasmon modes can couple with phonon modes? And this is Louis Tizay in our group, which has developed this experiment, schematized on the left, where you have a silver nanowire deposited on a layer of hexagonal boron nitride. And by measuring the response of the in the plasmon at the tip of the silver nanowire as a function of the length of the nanowire, you can study this coupling. For instance, we see it better on the next slide. When you move, when you change the length of the wire, on the top you will get only the mode of the silver nanowire, the plasmons. But then when you go across, you go and you can go mix your mode, your plasmon modes with the phonon modes in the bottom, the experience, and in the center, when you are for given length, you can have a strong coupling, which shows that you have two peaks on the plasmon peak, which goes into a phonon peak. And this is demonstrated very well on the curve, on the right, where you have the plasmon mode, which couple with the phonon modes. Plasmon mode increase like the velocity of the light, and the phonon mode is horizontal. This is a summary of the performance of STEM EELS from the early days. For instance, the 60s, what was done in Orsay and Cambridge at the same time. So we had an energy resolution of a couple of EV, 510 EV, a spatial resolution of 510 nanometers, and along in years, this is summarized on the right, we are going with successively the aberration correctors input, the motochromators and spectrometers input. We come to the situation now in half, which is a combination as introduced by Krivanek in Seattle in this non-microscope, now of typically 0.1 nanometer and 1.1 EV, or 1 nanometer and 0.01 EV. So this is an evolution. So before ending, I want to move a little out of EELS and to see how we can play with light, output, input. So the introduction in Orsay was developed by Mathieu Kosiak and other collaborators in Orsay. The idea is in the STEM column to introduce an optical mirror and to pick the light and to detect it. So this was the development, and now it is commercially available with Atolact. But you can pick the light out, or you can send inside a variable light laser, a laser variable length. So there is with this CL spectroscopy, and we can make different things. This is again the scheme of the neon Hermes machine, and now we focus on the exit of photons from the CL mirror. After the exit there, you can put in B a spectrometer, in C a polarizer, a filter of the angle, you can couple them. And finally, in E, you can make a beam splitter and then make a correlation in time of them and make a correlation of the statistics of the photons leaving the specimen. So these are brand new openings which are brought now with this multi-signal. We move from the EELS to photons. The bandwidth is much more narrow because we are photons detectable. This is now a few EV around the visible, but it is very rich. As an example, here you see the back of this image in blue crystal of boron nitride. In red, when you focus when you look, you have two signals coming out, the spectrum of the light coming of this object and time correlation of this object. And all this signal comes from the red spot, which is a defect in the boron nitride flake. So this defect emits photons, and you can measure the photon wavelengths, the distribution of the photon energy. This is a spectrometer, and you can measure the photon statistics of output. And in this photon statistics, what is very good is that instead, when you have a zero delay between the two signals, you have no, or we go towards zero. It means that from this source of photons, you cannot have two photons at the same time. So these are typically a source of single photons. And this has very good meaning for people in atomic physics and these photons. Basically, this slide summarizes many different studies which we can do with cathodoluminescence in different systems. So in looking at plasmons, because plasmons also emit photons, looking at photons in semiconductors with gap variations and point defects. So this is a whole subject when you have a summary by Mathieu Kossiak in 2017. Now, to finish, we will try to make a couple of information combining EELS and cathodoluminescence. So this is a cubic boron nitride specimen, which you see its image in the middle of the right column. If you look at the EELS spectrum, you have the full EELS spectrum. So with the plasmons around 20, 25, 30 eV. You look at the optical gap, which is in the 8 to 10 eV, and you look at the phonons, which is at 0.15 eV, so 150 millivolts. So this is really an hyperspectral information. So this is the information from this. Now, if you look at the cathodoluminescence, you see that the cathodoluminescence comes from a defect, which in this case is a Frankel pair defect. And this defect emits light, and this light, you have the spectrum on the top. We have a typical zero phonon line at N, lights accompanied by phonons. And the difference in energy in the cathodoluminescence separated by 150 millivolt is the one that you have measured by EELS. So there is a very good combination and support between EELS and cathodoluminescence. This is again the case on a single layer of tungsten disulfide, which is presently under study in the lab by Noémie Bonnet and Wistizide. They show measured with chromatem on the same nice small part of the specimen, a monolayer of decalcogonide. You can measure excitons at 2 eV, XA and XB, and you find them in the cathodoluminescence. You find the XA and a small and a nice, the energy resolution is better in cathodoluminescence, but the spatial resolution is not as good. Okay, we come to the conclusion now. These are a few selected projects which are now under active progress in the lab in Orsay. I am not at all involved in them now myself, but I follow always with the highest interest what's going on. And I have listed a few of these new ways of research in Orsay. The first one is detectors, EELS detector. In particular, like in many places around the world, we are testing for EELS, the use of direct electron detection cameras. The second point is now with all the techniques that we are to acquire data, spectrum imaging, we can make very fast acquisition and huge data amounts. So we are developing techniques to process them efficiently. We are also looking at sparse acquisition. This is very important for sensitive, beam sensitive specimens. So instead of acquiring many pixels, we acquire a limited number of pixels and develop tools to recover the information between them. This is recovering missing pixels. There is also a big effort now to develop random scanning modes by Marcel Tancet and co-workers. So there, instead of following the standard scanning mode line by line, now we go randomly from different points. And finally, we move more and more in the nano-laboratory domain, so with specimen stage and environment. And I will show examples with the red stars in there to finish. So a direct electron detector for EELS spectroscopy. We are testing a detector MEDIPIX, which is developed by quantum detectors. So the particle goes through a rather thick silicon material and create a number of electron hole pairs, and they are all detected read individually. So this is a signal, and this is this detector mounted on the neon machine, the head of the spectrometer there. And just to show an example, there we see that you can have a very large dynamic range. So you can make map from the zero loss. You see, the scale is 10 to the 9, and at the end, the scale is 10 to the 5. So this is a spectrum acquired with this detector, quantum detector. And these are maps. You see that you have atomic resolve maps with the different signals: titanium, manganese, oxygen, and lanthanum, which you see on this scale. So typically, these images have been recorded with 50 picometer step, 1 millisecond acquisition time per spectrum, and 30 picoamp. So these are very broad and development by Alexandre Glotter and Marcel Tancet. About random scan, so this is a slide prepared by Nathalie Brun. So random scanning with the neon. So there, it's not a random scan, but it is scanning and sampling, a random scanning sampling. You see there dark field image on the left, the one random spectrum. So, and then in this whole spectrum, which you see on the right, there is a lot of noise, but we reconstruct a spectrum image of the different components using a new methods developed in collaboration with University of Toulouse. About the final example, so now the specimen can be illuminated by a laser. So a laser illuminating, you put your specimen in an excited state, and you create emission. And then, so there, and in this emission, you can show that you can create electron energy gain. So you dress your specimen with plasmons, and you can see that another electron can excite, can gain the energy of this plasmon. So this is what is demonstrated on this slide. This was a paper published by Das last year, and you will see it better there. The stimulated electron energy gain, you see one spectrum on the left. So now you have the zero loss, and you have a spectrum containing on the left energy gain, on the right energy loss with your laser illumination. So, and you see that changing the wavelengths, this is what is brought new with this experiment, changing the wavelengths by 15 nanometer, which is a 3 image on the right. You go from 585 to 600 and 650 wavelengths of the laser. You can see that you excite plasmons at a different position on the edge of your specimen, and you have high resolution energy because you change your energy length by 15 nanometer, so 15 millivolt resolution. Last but least, now going to environmental. So the idea is to introduce, for instance, one of the first example is to introduce specimen stage at variable temperature, and liquid nitrogen for the moment, and we are expecting soon liquid helium stage. So, and the first example studied by Laura Baucher there is a transition in V2O3, metal insulator transition. you see the phase diagram on the left, and you go from along the yellow arrow from a paramagnetic metal to an antiferrometric insulator at a temperature of the order of 137 K. And what you can see, this is the specimen stage, and the specimen stage, you shows two spectra, and you see the fine chains in particular on the bottom of the oxygen KH. So you have on the center the vanadium edge and the oxygen KH. And if you look at detail, you see a fine structure change at about 550. 534 EV and a shift of 520 millivolts. So this was just a short review of the new openings of these microscopes in terms of big data, data acquisition and processing, specimen environment, electron energy gain, phase change. So there is a board, and I expect for sure that in the next few years there will be many new good and stimulating successes coming out of electron energy loss, hyperspectral, multi-signal in combination with phonons and photons. And what I have shown today in my talk has been acquired by a group, of course, a very dynamic and successful group. For instance, there is a picture a couple of years ago where you see the chief in the center, Odile Stéphane, our group leader, Mathieu Kossiak, who won the FEI prize, European prize in 2012, Marcel Laureate, who was the first laureate of the French Society Microscopy, Raymond Castin Prize, the founder of all microanalysis. And these are all the group people in the group now who have produced all the results which I have shown and discussed today. Let's say thank you for your attention and to Electron Microscopy of India prize support. Thank you. Alors là, il faut que je vois.
Thank you very much, Professor Colliex.
I don't see you. We're looking for you.
Yeah. You able to see me?
No, we have lost you. Okay. You are somewhere. Okay.
Yeah. So thank you very much for giving this very enlightening and very informative lecture. I wish if I can see Professor Ranganathan, Professor Chattopadhyay, Dr. Day, very senior professors, starting from very senior professors to very young researchers who have joined this.
Very mixed population. Good.
Yeah. Very mixed population, and very young researchers have also joined. I'm sure they would have enjoyed and they would have learned a lot. And now, if you agree, we can take few questions quickly before we summarize.
Okay.
Yeah.
Very key to understand them.
Yeah. So if there is any question, it's welcome. Anybody has any question right now? Otherwise, Professor Colliex email is always available with us.
You can send questions to my email address, of course.
Yeah.
So, lockdown, you see, this is a unique day. I am for the first time back in my office in Orsay after nearly 4 months out, but I hope.
Okay. So thank you for putting all efforts coming from Normandy to Orsay.
Oh, yes, yesterday. Yes.
Yeah.
Okay. So, but I was very happy to give this talk in front of all of you, and I hope, yes, when I gave a talk in Hyderabad about 4 months ago, yes, at the end, many young people came to me and say, "Oh, we have to learn a lot of you." So I think that is a compliment.
Yeah.
And I hope it will stimulate a lot of new vocations to use for many purposes this generation technique.
Yeah. So that was very nice. Now, if there is no query right now, I may request Dr. Satish to say vote of thanks before
Thank
we
you.
close down. Dr. Satish?
Yes, sir.
Professor Kamani Chattopadhyay, you want to say something? I can see you here. We are not able to hear you. Your mic is mute.
There is so much of information in Professor Colliex's talk. It requires time to digest.
I am sorry. But this subject is very active now, and as you have seen in Orsay, we have a group of 20 people about, and they are all active. So we have a tradition of developing new techniques, instrumentation, and solving problems in many domains. So that makes a rich diversity from now aggregations in biological cells to nanotubes and theory domains.
Yeah, I think opportunity is enormous, but one has to really look at how we can use all the spectrum of informations to solve some problems.
Yeah, sure.
This is typically our job there is to see how we can use a technique to solve a problem. This has been behavior over 40 years. To see, I was welcoming people, they were explaining the problem, and I was trying to develop them for 40 years. And this is a good continuation. There is a super group that to continue in this way.
So thank you very much. Dr. Satish, can you say a vote of thanks now?
Yes, sir.
Before we disconnect? Yeah. Satish, please.
Yes, sir. Thank you, sir. First, I would like to thank Professor Colliex for such a wonderful lecture, where actually he has covered from electron energy loss spectroscopy and the combination of several new spectroscopic techniques, which is used very well for the in nanomaterials characterizations. These are like very advanced technologies, and which we would like to learn, and we are enlightened by the works and the Professor Colliex lecture. And then we hope we all will be able to use this technologies in future, and will be able to address several unknown features which is hidden in the Nano-World. Then I would like to thank all the distinguished members of EMSI and the council members and all the senior professors present here. They are also present in YouTube as well, and and I would like to also thank all the EMSI members who was present in Zoom as well as in the YouTube live. And I would like to thank our director CSIR-AMPRI, Dr. Avinash Kumar Srivastava, and also would like to thank, he is also president of EMSA. And I would like to thank him for his wonderful arrangement. And I would like to thank all the people who has worked for the arrangement of this thing. And finally, I would like to thank all the participants who are there in the YouTube as well as in the Zoom, and participating and like listening to this lecture for 1 hour lecture. And I would like to thank all of you for a wonderful evening, and have a nice evening.
Okay. So have you recorded my presentation?
Sure, it must be.
Yes, sir. It is recorded.
It is recorded, so I don't need sending it to you. Okay. So,
Yeah, and it will be available on YouTube also. Anytime anybody can open and go through.
Work and watch.
And we will send you a copy of that.
Okay, good. Okay.
So thank you very much to everybody.
And good evening to all of you.
Good evening to everybody.
Take care. Come
Bye.
out of COVID. Take care.
Thank you. Take care. Stay safe. Thank you.
Okay.